Tonight we are going to answer a question that sounds like it should have been answered a long time ago. How big is the Milky Way? You probably know a number. 100,000 light-years across. It is the number in textbooks, the number on diagrams, the number repeated in classrooms for decades. And for just as long that number has been wrong. Or rather, it has been describing only a small piece of something much larger. The reason we got it wrong is not because astronomy failed. It is because of where we are standing. We are inside the galaxy. We cannot step outside it and photograph it as a whole. Every measurement of the Milky Way's size has been a reconstruction, an attempt to describe the shape of a building while sitting in one of its rooms. New tools changed that, and when they did, the number did not get slightly larger. It expanded dramatically, then expanded again, and then again, as each new layer of the galaxy revealed itself to instruments that could finally see it. By the end of tonight, you will understand not just how big the Milky Way actually is, but why the answer kept changing what each new measurement was actually finding, and why the final number is not one number at all. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. On a clear night, far from any city, the Milky Way stretches across the entire sky. Not a portion of it, all of it. From one horizon to the other, a band of faint, dense light arches overhead in a complete arc of 180 degrees. It is the most overwhelming sight in the natural world, not because it is bright, but because of its scale. It takes up the whole sky. It surrounds you. And that, precisely, is the problem. What you are seeing when you look at the Milky Way band is the plane of our galaxy's disk, viewed from the inside. You are embedded in that disk. The stars you see scattered across the band are your immediate neighbors, the closest few hundred to a few thousand light-years in each direction along the plane. Beyond them, more stars. Beyond those, more still. And eventually, in every direction along that plane, the star density thins out and the disk fades into something else. But you cannot see where it ends. You are too deep inside it to see the edges. This is fundamentally different from how we study every other galaxy in the universe. The Andromeda Galaxy is roughly 2.5 million light-years away. At that distance, it appears as a faint smear of light in the constellation Andromeda. Small enough that you can cover it with your extended thumb. With a camera and a long exposure, you can photograph its spiral arms, its central bulge, its surrounding halo of older stars, its pair of small satellite galaxies. You can see Andromeda as a complete object. You can trace its extent from one edge to the other in a single image and ask how far across it is. For the Milky Way, that photograph does not exist. No spacecraft has ever traveled far enough from Earth to capture the galaxy from outside. No instrument has ever looked back and seen the Milky Way whole. We are inside it, and we have always been inside it, and every measurement of its size has had to be made from this single embedded vantage point. Think about what that means in practice. To measure the size of the Milky Way, you cannot look at it. You have to look through it, in all directions, and from what you find, reconstruct what you cannot directly see. You measure distances to individual stars, which requires techniques that become unreliable at large distances. You measure the brightness of specific types of stars whose true luminosity you know, which requires correcting for the dust between you and them that absorbs and dims their light. You measure the chemical composition of stars to determine which population they belong to, which requires spectroscopy detailed enough to identify elements in starlight from tens of thousands of light-years away. And here is the complication that made all of this harder than it sounds. The galaxy is not empty between the stars. It is filled with gas and dust, concentrated primarily in the same plane as the disk. When you look outward along the disk, you are looking through a column of obscuring material that blocks, scatters, and dims the light from distant stars. The more distant the star, the more dust between you and it, the harder it is to measure accurately. Looking toward the galactic center, roughly 26,000 light-years away in the direction of the constellation Sagittarius, means looking through more intervening dust than in almost any other direction. Radio waves pass through the dust relatively unimpeded, Infrared light is less absorbed than visible light, but ordinary starlight, the kind the eye sees and early telescopes collected, is severely attenuated along the galactic plane. The consequence is that for most of the history of Milky Way astronomy, the measurements available were limited to the portion of the galaxy that visible light instruments could reach. The outer disk was harder to characterize because the stars there are fewer, fainter, and seen against a background of dust that blurs and dims the signal. The 100,000 light-year number emerged from this limited window. It was a real measurement of a real structure, but it was measuring the galaxy's densest, most easily visible region, and assuming that region told the whole story. It did not. The inside problem is not merely a challenge of distance, it is a challenge of perspective that has no easy workaround. Consider what it means to map a forest from inside it. You can walk in any direction and count the trees you pass. You can note when the trees become denser or sparser. You can identify different species, measure their heights, estimate their ages, but you can easily determine the total area of the forest or find where its boundary is. The trees close to you are well mapped. The trees at the edge of the forest are uncertain. You have to walk far enough to find them, and walking that far takes time you may not have. Now add one more complication: fog, dense in some directions, thin in others. In the foggy directions, even the nearby trees are hard to see clearly. In the clear directions, you can see further, but you know the fog is out there somewhere, and the trees in the foggy directions are undercounted. This is the problem of Milky Way astronomy. The dust plays the role of the fog. It is not uniform, it is thicker in the plane of the disk and thinner away from it. Observations made perpendicular to the disk, looking out of the plane of the galaxy, are relatively unobscured. Observations made along the plane, in the directions where most of the distant disk stars lie, pass through the thickest concentrations of dust. The result is a galaxy that is well measured in some directions and poorly measured in others. The stellar counts that produced the 100,000 light-year estimate were not wrong as a description of the best observed parts of the galaxy. They were incomplete as a description of the whole. For decades, this incompleteness was accepted as an unavoidable limitation. The tools available simply could not reach far enough or see clearly enough through the dust to characterize the outer disk. What changed was not the galaxy. What changed was the instrumentation. There is one more dimension of the inside problem worth naming. It affects not just the measurement of the disk's extent, but the measurement of nearly everything about the galaxy's structure. When you observe an external galaxy, you see the whole thing at once. The near side and the far side are both in your field of view simultaneously. If one part of the galaxy is obscured by dust within the galaxy itself, you can see around the obscured region by shifting your vantage point slightly or by using complementary wavelengths. The galaxy is a complete object that you can study from multiple angles. For the Milky Way, there is only one vantage point. Earth, and by extension the Sun, is fixed at one location inside the disk. You cannot observe the galaxy from any other angle. The near side of the galaxy, the stars within a few thousand light-years, is well studied because the stars are bright and nearby. The far side of the galaxy, opposite the galactic center from Earth, is significantly harder to study because you are looking through the entire thickness of the disk, including the galactic center itself, with its concentrated gas and dust. The zone of avoidance, as it is called, is the band of sky along the galactic plane, where dust extinction is so severe that optical surveys are effectively blind. Every external galaxy we study can be characterized from multiple angles using telescopes on Earth at different times of year, or in principle by spacecraft at different locations of the solar system. The Milky Way cannot. Our single embedded vantage point is both the starting point and the ultimate constraint on Milky Way astronomy. The number 100,000 light-years did not come from a single moment of discovery. It came from a long accumulation of measurements, each one improving on the last, each one working within the constraints of the instruments and techniques available at the time. In the early 20th century, the astronomer Harlow Shapley used a particular type of pulsating star called a Cepheid variable to map the positions of globular clusters, dense balls of ancient stars that orbit the Milky Way at large distances. Cepheid variables have a useful property. The period of their brightness fluctuation is directly related to their true luminosity. Measure how long it takes a Cepheid to complete one brightness cycle, and you can calculate how intrinsically bright it is. Compare that to how bright it appears from Earth, and you can calculate its distance. Shapley used this technique to locate dozens of globular clusters scattered across the sky, and from their distribution, he inferred the position of the galactic center and the rough size of the galaxy center. Shapley's result was too large, roughly 300,000 light-years across. He did not fully account for the fact that dust in the galactic plane was making distant Cepheids appear dimmer than they truly were, which made them seem farther away than they actually were. When the dust correction was properly applied decades later, the numbers came down significantly. By the mid-20th century, the consensus had settled around roughly 100,000 light-years for the diameter of the galaxy's stellar disk. That number had a specific meaning. It referred to the size of the bright, star-dense region of the disk, the part where the number of stars per unit volume is high enough to be detected easily with the techniques available. It was not the size of everything the Milky Way contained. It was the size of its most visible, most easily measured layer. The concept behind the number is called the scale length. The density of stars in the disk does not simply drop to zero at some sharp boundary. Instead, it decreases gradually as you move outward from the center, roughly following an exponential pattern. The scale length describes how quickly that decrease happens, roughly how far from the center you need to travel before the star density falls by a factor equal to the mathematical constant E, approximately 2.7. For the Milky Way's disk, the scale length has traditionally been estimated at around 2.6 kiloparsecs, or about 8,500 light-years. A scale length of 8,500 light-years implies a total disk diameter considerably smaller than 100,000 light-years. If you follow the exponential curve all the way to very low densities, the quoted 100,000 light-year figure came from a different threshold, the distance at which the disk's visible star density becomes low enough to call it the edge. By whatever standard was being applied at the time, this is the subtlety that made the answer both real and incomplete. The 100,000 light-year number was not invented. It was measured, but it measured the galaxy's densest inner region under the specific conditions of the instruments that made the measurement. As instruments improved, as the ability to see further and detect fainter and more distant stars improved, the apparent edge of the disk moved outward. The galaxy did not grow. The measurement got better, and when a specific new technique arrived in the 2010s, one that could identify stars by their chemistry rather than just count them by their brightness, the edge of the disk moved outward in a dramatic way. The revision of the Milky Way's size has happened more than once. It is not a new story. Harlow Shapley's 300,000 light-year estimate was revised downward when dust extinction was properly accounted for. The subsequent 100,000 light-year consensus was refined several times as better distance measurements and better models of the disk's structure became available. Each revision brought the number into closer agreement with measurements from multiple independent techniques. What makes the current round of revisions different is not just the direction of the change, outward, always outward, as better instruments find previously invisible stars, but the nature of the new measurement techniques. Earlier estimates were largely model-dependent. They required assuming a particular mathematical shape for the density profile of the disky, typically an exponential decline, then fitting that model to the available data to extract the scale length, and then translating the scale length into a physical size using various conventions. The scale length approach has a built-in limitation. An exponential profile, by its mathematical nature, never reaches zero, it just gets smaller and smaller. So the question of where the disk ends is always partly a question of what threshold you decide to call the edge. Different thresholds give different answers, and different instruments, with different sensitivities, effectively set different thresholds by virtue of what they can and cannot detect. The spectroscopic approach used in the 28 study is less model-dependent in a crucial way. Instead of assuming a density profile and fitting it, it identifies individual stars as disk members by their chemistry and asks how far they are from the center. The furthest confirmed disk stars set a lower bound on the disk's extent. That is not a model result, it is a direct observation. Stars at 81,000 light-years from the galactic center with the metallicity of disk stars are disk stars. No modeling assumption changes that. This is why the 200,000 light-year figure represents a qualitative improvement over the 100,000 light-year figure, not merely a quantitative one. The scale-length concept has one more implication worth making explicit. Because the disk's stellar density declines exponentially with distance from the center, most of the disk's stars are concentrated in the inner region. The outer disk contains stars, but at a much lower density. This means that the outer disk contributes only a small fraction of the total stellar population, even though it occupies a large volume. A disk with a scale length of 2.6 kiloparsecs, about 8,500 light-years, has half its stars within about 1 scale length from the center, and most of its stars within 2 or 3 scale lengths. Stars beyond 5 or 6 scale lengths from the center are a small fraction of the total. This is why the outer disk is hard to detect by star counting. Even though it is physically there, its contribution to the total count in any given field of view is small. This also means that measuring the disk's outer extent by star counting sets a threshold that depends on the survey's sensitivity. A shallower survey, one that can only detect relatively bright stars, will set its threshold at a shorter distance, finding fewer outer disk stars and concluding the disk ends sooner. A deeper survey, one that can detect fainter stars, will find outer disk stars at larger distances and conclude the disk extends further. The result is that the measured outer edge of the disk moves outward as survey depth improves. The spectroscopic approach partially sidesteps this issue by not relying on counts of stars at a particular threshold. It asks whether a given star at a given distance has the chemistry of a disk star, without requiring that stars of that type be dense enough to exceed a detection threshold. In 2018, a team of researchers from the Instituto de Astrofísica de Canarias in Spain and the National Astronomical Observatories in Beijing published a study that changed the number significantly. Their approach was different from simply looking for stars and counting them. Instead, they analyzed the chemical compositions of more than 4,600 stars using data from 2 large spectroscopic surveys, APOGAE, which is the Apache Point Observatory Galactic Evolution Experiment, and LAMOST, the Large Sky Area Multi-Object Fiber Spectroscopic Telescope. Spectroscopy breaks starlight into its component wavelengths, revealing absorption lines produced by different chemical elements in the star's atmosphere. From these lines you can determine how much of each element the star contains. Its chemical fingerprint. The key chemical signature they were looking for was metallicity, the relative abundance of elements heavier than hydrogen and helium in a star's spectrum. This matters because different stellar populations have different metallicities. Stars in the disk tend to be metal-rich. They formed from gas that had already been enriched by many generations of previous stars, whose supernovae scattered heavy elements into the surrounding medium. Stars in the halo, the diffuse cloud of ancient stars surrounding the disk, tend to be metal-poor. They formed very early in the galaxy's history, when the gas had not yet been significantly enriched. By measuring metallicity, you can tell which population a star belongs to, even when you cannot directly assess its orbital shape or its position relative to the disk. Using this chemical fingerprint, the researchers identified disk stars, stars with the metallicity characteristic of the disk population, at distances far greater than the previously assumed boundary of the disk. The prior accepted limit had placed most confirmed disk stars within roughly 50 to 60,000 light-years of the galactic center, corresponding to a disk radius of about that distance. The new study found spectroscopically confirmed disk stars at distances exceeding 81,000 light-years from the center. Lead author Martín López Corredo Reyra stated the finding plainly: as far as we know, nobody could previously say that stars farther than 81,000 light-years are confirmed spectroscopically to belong to the disk. The disk did not thin to nothing at 50,000 light-years from the center. It continued. The total diameter of the stellar disk, according to this study, was approximately 200,000 light-years, twice the schoolbook number. The doubling sounds dramatic, but it becomes understandable once you grasp what the earlier measurements were actually finding. They were finding the high-density core of the disk, the region where stars are packed densely enough to be easily detected by brightness surveys. The outer disk is real, it simply has a much lower density, making it harder to detect by counting stars alone. The chemical approach, which could identify individual disk stars regardless of their density in the region, reached further and found what was always there. This revised disk diameter is not universally adopted as the standard figure in all sources, and the precise boundary depends on where you set the density threshold. But the spectroscopic confirmation of disk stars at these distances is the strongest direct evidence of the disk's true extent currently available. The disk is at minimum 100,000 light-years in radius from the galactic center. Its full diameter is approximately 200,000 light-years. The schoolbook number described half the disk. The chemical distinction between disk stars and halo stars reflects a genuine physical difference in their histories. When the universe was young in its first few billion years, the galaxies that would eventually become the Milky Way were just beginning to form. The gas that collapsed to form the first stars was almost entirely hydrogen and helium, the elements produced in the Big Bang. The first stars were therefore extremely metal-poor. They formed from gas that contained almost no elements heavier than helium. As these first stars aged and exploded as supernovae, they scattered their processed interiors into the surrounding gas. The gas became progressively enriched in carbon, oxygen, silicon, iron, and other heavy elements forged inside stars or during the supernova explosions themselves. Each new generation of stars formed from gas already enriched by previous generations. Stars in the stellar halo are old enough that they formed when this enrichment process was still in its early stages. They carry the chemical signature of the early universe: low metallicity, high ratios of oxygen, and other elements produced in massive stars relative to iron, which accumulates more slowly. Their chemistry is a timestamp. Stars in the disk are younger or formed over a longer period from gas that have been continuously enriched. They carry higher metallicities, closer to the Sun's own composition. The Sun, formed about 4.5 billion years ago, is a relatively typical disk star in its chemical composition. This chemical difference is not subtle. It is large enough to be measured clearly in a stellar spectrum, even for a star tens of thousands of light-years away. When the 2018 study found metal-rich stars beyond 81,000 light-years from the galactic center, it was not a borderline case. The chemical fingerprint clearly identified them as disk stars, not halo stars, not borderline population members. The disk extends that far. The chemistry confirms it directly. The metallicity gradient, the way stellar metallicity changes with position in the galaxy, is itself a tool for understanding the galaxy's formation history. In the disk, metallicity decreases with distance from the center. Stars close to the galactic center tend to be more metal-rich than stars in the outer disk. This is expected. The inner galaxy formed more stars earlier, recycled more material through stellar evolution and supernovae, and accumulated heavier elements more rapidly. Stars that formed in the inner disk at later times formed from more enriched gas than stars that formed in the outer disk. The metallicity gradient confirms that the disk is a single connected structure rather than two separate populations that happen to have overlapping distributions. The chemical properties change smoothly and continuously from center to edge, consistent with the idea that the disk formed from the inside out, the inner regions first, the outer regions later, as gas cooled and settled into the rotating plane. The exact slope of the metallicity gradient and how it changes with stellar age are currently active areas of research. Gaia data, combined with large spectroscopic surveys like APOGE and LMOST, have enabled the most detailed characterization of this gradient to date. The 2024 Half-Light Radius study was itself built on this data, using age-resolved populations to trace how different stellar age groups contribute to the disk's surface brightness profile. The metallicity gradient is one of the ways in which the disk carries its own history encoded in the chemistry of its stars, a record of where and when star formation happened across the full span of the galaxy's existence. The disk is bigger than the textbook said, but the disk is also not the shape the textbook showed. Every diagram of the Milky Way you have ever seen depicts it as a flat spiral, a thin, smooth pancake with a central bulge and elegant arms curving outward. This is a useful approximation, but the actual disk is neither flat nor smooth, and the differences matter for understanding the galaxy's true extent and its history. The most significant departure from the flat pancake model is the warp. Astronomers have known since the late 1950s that the Milky Way's disk is warped. The evidence came originally from radio astronomy, specifically from mapping the distribution of neutral hydrogen gas, which emits a characteristic radio signal at a wavelength of 21 centimeters. This signal travels through dust unimpeded, allowing radio telescopes to trace the gas distribution across the entire galaxy in a way that optical telescopes could not. When radio astronomers mapped the neutral hydrogen, they found that the outer disk did not follow a flat plane. Instead, it bent upward on one side of the galaxy and downward on the other, creating an S-shaped curve when viewed edge-on. The brim of a fedora hat bending up on one side and down on the other is a reasonable visual analog, not folded sharply but gradually and pervasively curved. The warp extends across the outer disk, becoming more pronounced at larger radii from the center. Its origin is still debated, but the leading explanation involves the dark matter halo, the vast invisible sphere of mass surrounding the galaxy. If the dark matter halo is slightly tilted relative to the disk's rotation axis, its gravitational field would exert a continuous torque on the outer disk, gradually bending it. The disk precesses under this torque, like a spinning top wobbling slowly under the influence of gravity. The warp completes one slow rotation around the galactic center over roughly 600 to 700 million years. The warp was confirmed and mapped in detail by a 2019 study using classical Cepheid variable stars as tracers. Cepheids are among the most reliable distance indicators in astronomy because their brightness fluctuation period is directly tied to their true luminosity. The 2019 study used over 1,000 Cepheids spread across the outer disk and found that their three-dimensional distribution traces out exactly the S-shaped curve the radio data had suggested, but now confirmed in actual stellar positions rather than gas distribution alone. Beyond the warp, the disk also flares. The thickness of the disk, how much it spreads above and below the central plane, increases as you move outward from the center. Near the Sun, the thin disk is roughly 1,000 light-years thick. At the outer edges of the disk, this thickness increases considerably. Stars in the outer disk occupy a larger vertical range above and below the midplane. The flaring is likely caused by the decrease in the disk's own gravitational self-compression at large radii, where the density of mass is lower. And there is a third structural feature, more recently discovered. In 2025, Gaia data revealed that the disk is not only warped and flared, it is also corrugated. A wave-like ripple runs through the disk, with stars above and below the midplane in a coherent, large-scale pattern spanning tens of thousands of light-years. This is not random turbulence. The corrugation is structured, ordered, and likely the signature of an ancient collision. When a smaller galaxy falls into the Milky Way, its gravitational impact sends ripples through the disk, like dropping a stone into still water. The corrugation seen in Gaia data is still ringing through the disk hundreds of millions of years after the collision that caused it. Warped, flared, corrugated, and 200,000 light-years wide, the disk alone is already a more complex and extended structure than most visualizations show. But the disk is still just the densest, brightest, most easily seen layer of the galaxy. Beyond it, the structure continues. The corrugation wave found in Gaia data is particularly interesting because it points to an ongoing dynamic process rather than a static structure. When you look at a pond after dropping a stone, you see concentric ripples spreading outward from the impact point. These ripples are not permanent features of the pond. They are waves that propagate through the water and gradually dissipate. The corrugation in the Milky Way's disk is analogous. It is a wave, not a permanent deformation. Stars oscillate up and down through the disk midplane in a coherent pattern rather than randomly. The oscillation is too organized to be thermal noise. Something set it in motion. The most likely culprit is a dwarf galaxy flyby or collision, when a small galaxy passes close to the Milky Way's disk or plunges through it. The gravitational impulse sets up oscillations in the disk that propagate outward over time, much like ripples spreading from a stone dropped in still water. The Sagittarius dwarf galaxy, which has been orbiting the Milky Way for billions of years and has passed through the disk multiple times, is a candidate. But other passages by other small galaxies in the past cannot be ruled out. The corrugation wave spans tens of thousands of light years and involves coherent motion of millions of stars. The fact that it is still detectable means it is geologically recent. If it had been oscillating for billions of years, it would have spread and damped out. The wave we are seeing in Gaia data was probably set in motion within the last few 100 million years. This is one of many ways in which Gaia's data revealed the Milky Way to be a dynamic, actively evolving structure rather than a settled, stable disk. The galaxy is alive in a way that its apparent serenity on the night sky does not suggest. The warp's slow precession has an interesting observational consequence. Because the warp rotates around the galactic center over 600 to 700 million years, the direction in which the disk bends upward and downward changes over geological time. What we observe today, one side of the outer disk elevated, the other side depressed, is only the current phase of this precessing structure. In a few 100 million years, the orientation will be different. The stars currently elevated above the midplane on one side of the galaxy will have precessed partway around, and a different part of the outer disk will be elevated. From the perspective of any star in the outer disk, the warp appears as a slow oscillation, the disk periodically rising and falling as the warp precesses past. For stars at the Sun's distance from the center, the warp's effect is modest. We are not far enough out to be significantly displaced from the midplane, but for stars in the outer disk, beyond about 30,000 light-years from the center, the warp displacement can be substantial. Stars in the most elevated regions of the outer disk can be thousands of light-years above the midplane that the inner disk traces. This vertical displacement adds to the flaring. The outer disk stars are spread over a larger vertical range both because of the flaring, the disk genuinely thickening, and because of the warp, the disk tilting at different azimuths. The two effects combine to make the three-dimensional structure of the outer disk considerably more complex than any flat disk model represents. If you could somehow rise above the plane of the Milky Way, far above it, tens of thousands of light-years up, looking back at the disk from a position in empty space, you would see the spiral arms curving outward, the central bulge glowing with densely packed ancient stars, the disk fading gradually at its edges. And then, surrounding all of it, you would see something fainter and more diffuse. A ghost shell of stars, sparse, scattered, following orbits that do not respect the flat plane of the disk. These stars move in great elongated loops that carry them high above and far below the galactic midplane, in orbits that are inclined at steep angles to the disk, or stretched into radial paths that bring them close to the galactic center before swinging far out into the surrounding space. They are not disk stars. They belong to a different structure, older, more spread out, less organized, called the stellar halo. The stellar halo is ancient. Most of its stars are 10 to 13 billion years old, among the oldest in the galaxy. They are metal poor, formed when the galaxy's gas had not yet been enriched by many generations of stellar evolution and supernova explosions. The disk stars around the Sun formed from gas that had been recycled through many stellar generations, accumulating heavy elements along the way. Halo stars formed before most of that enrichment happened. Their chemical compositions carry the signature of the very early universe. These ancient stars orbit the galactic center in large, often highly elongated paths. Some of them pass close to the galactic center at the inward extreme of their orbits. Others swing out far into the surrounding space before being pulled back. Together they form a roughly spherical distribution, not a flat disk, but a three-dimensional cloud, centered on the galactic center, extending outward in all directions. How far does it extend? The stellar halo is not easy to measure because it is so diffuse. Near the Sun, halo stars are rare compared to disk stars. One way to trace the halo's extent is to look for particular types of stars that can be reliably identified at large distances. RR Lyra variables, which are pulsating stars similar to Cepheids but older and more metal poor, and K giants, a class of red evolved stars. By finding these traces at progressively larger distances, astronomers can map how the stellar density changes as you move out through the halo. Current measurements place the extent of the stellar halo at roughly 400,000 to 600,000 light-years in diameter. Some individual stars have been found at even greater distances beyond 1 million light-years from the galactic center. Though whether these extreme outliers are still gravitationally bound to the Milky Way or are simply passing through from outside is a question not yet fully resolved. Where do halo stars come from? Some formed in the early Milky Way itself during its first billion years of existence. but a significant fraction arrived from outside, stripped from smaller galaxies that the Milky Way absorbed over its history. When a dwarf galaxy falls into the Milky Way's gravitational field, the tidal forces of the larger galaxy stretch and disrupt it. Its stars are pulled apart and scattered into the halo, forming streams and shells that persist for billions of years before fully mixing into the background. The stellar halo is, in a very real sense, a graveyard of galaxies, the accumulated debris of dozens of smaller systems that the Milky Way consumed over its lifetime. The most prominent current example is the Sagittarius dwarf galaxy, a small satellite galaxy that is currently being disrupted by the Milky Way's tidal forces. Its stars are being stretched into a vast stream that wraps around the galaxy in a great arc, visible in the positions and velocities of distant stars in the halo. The Sagittarius stream is a real-time demonstration of the process that built much of the halo. Smaller galaxies falling in, being torn apart, their stars joining the Milky Way's extended stellar envelope. At 400,000 to 600,000 light-years in diameter, the stellar halo alone is 4 to 6 times wider than the 100,000 light-year number most people associate with the Milky Way, and this is still not the full extent of the galaxy. The term stellar halo can give a misleading impression of uniformity. The stellar halo is not a smooth, featureless cloud of evenly distributed stars. It is highly structured, filled with streams, shells, overdensities and clumps, each one the remnant of a past merger event. When a dwarf galaxy is disrupted by the Milky Way's tidal forces, its stars do not simply spread evenly through the halo. They form a stream, a coherent ribbon of stars following roughly the same orbital path as the original galaxy's orbit. This stream persists for billions of years before the stars gradually disperse and mix into the general halo background. During its lifetime, it is detectable as a slight overdensity of stars along a particular path in the sky, moving with similar velocities. The Sagittarius stream is the most prominent. It has been mapped as a great circle around the entire galaxy, looping nearly completely around the Milky Way. It consists of at least 2 wraps, material stripped from the Sagittarius dwarf galaxy during 2 different orbital passages. Stars in the stream are identifiable by their positions, velocities, and chemistry. The Monoceros ring is another structure, a wide ring of stars in the outer disk that may represent the disrupted remains of a dwarf galaxy, or may be a feature of the warped disk itself. The Anticenter stream, the Virgo overdensity, the Hercules Aquila cloud, each is a named feature of the halo that represents either the debris of a past merger or a large-scale overdensity whose origin is still being investigated. Gaia's data transformed the study of these structures by providing precise positions and velocities for millions of stars in and around them. Before Gaia, halo structure was traced by photometric surveys, measuring the brightness and color of stars across patches of sky. After Gaia, each star also had a precisely measured distance and a proper motion measurement, giving a 3-dimensional velocity. The halo went from a 2-dimensional map to a 6-dimensional dataset. 3 dimensions of position, 3 of velocity, and the substructures within it became dramatically clearer. The stellar halo's 2 origin channels, in situ formation and ex situ accretion, leave different chemical and kinematic signatures that can be used to separate the 2 populations. Stars that formed in the early Milky Way itself tend to have a particular range of metallicities and orbital properties consistent with having formed from the galaxy's own gas at an early time. They may have somewhat higher metallicities than the most extreme halo stars, and their orbits may be less radially extreme because they formed in a potential that was already roughly centered on the galactic center. Stars accreted from other galaxies carry the chemical signature of their origin galaxy. Dwarf galaxies have their own metallicity-luminosity relation. Smaller galaxies tend to be more metal-poor than larger ones. A star that formed in a low-mass dwarf galaxy will typically be more metal-poor than a star that formed in the early Milky Way itself, even at the same age. This chemical difference allows the 2 populations to be partially separated in surveys. The kinematic difference is also useful. In situ halo stars formed from gas that was already broadly co-rotating with the nascent Milky Way disk, so they tend to have some residual prograde motion. Accreted stars from random satellite infall tend to have more isotropic orbital distributions, equal numbers orbiting prograde and retrograde. The ratio of prograde to retrograde orbits in the inner halo is therefore a measure of the relative contribution of in situ and accreted stars. Current analyses suggest the inner stellar halo is dominated by accretion, particularly from the Gaia Sausage Enceladus event, while the outer halo may have a larger contribution from later, more random accretion events. In December 2013, the European Space Agency launched a satellite into an orbit around the Sun called the L2 point, about 1 million miles from Earth in the direction away from the Sun. Its name was Gaia. Its mission was to measure the positions, distances, and motions of stars with a precision that no previous instrument had approached. Before Gaia, the most precise catalogue of stellar positions and motions contained about 100,000 stars measured to high accuracy. Gaia's first major data release contained precise measurements for roughly 1 billion stars. Its subsequent releases expanded this to approximately 1.5 billion. The positional accuracy, how precisely Gaia could determine where a star sits in the sky, was measured in micro-arcseconds, millionths of an arcsecond, a unit so small that 1 micro-arcsecond corresponds to the angular size of a €1 coin viewed from a distance of 38,000 kilometers. This precision made possible a technique called parallax, applied at galactic scales. Parallax is the apparent shift in a nearby object's position when viewed from different vantage points. Hold your finger in front of your face and close one eye, then the other. Your finger appears to jump relative to the distant background. Stars do the same thing as Earth orbits the Sun. Nearby stars appear to shift slightly relative to distant background stars over the course of a year. The size of this shift depends on the star's distance. Closer stars shift more distant stars shift less. By measuring the shift, you can calculate the distance. Before Gaia, parallax measurements were reliable to distances of a few thousand light-years at most. Gaia extended the range to tens of thousands of light-years. Combined with the spectroscopic data from other surveys, Gaia's distance measurements gave astronomers a three-dimensional map of the Milky Way with detail and precision that had simply not existed before. Gaia also measured proper motion, the slow drift of each star across the sky as it follows its orbit around the galaxy. This gives a second dimension of velocity, complementing the line-of-sight radial velocity measured by spectroscopy. With both components, the full three-dimensional velocity of each star can be reconstructed. And from velocities, you can infer gravitational forces. From gravitational forces, you can infer mass distributions. From mass distributions, you can estimate the extent of components you cannot see directly, including the dark matter halo. The Gaia mission did not make a single transformative discovery. It made every measurement better, and in doing so, it unlocked dozens of discoveries that were waiting for the data quality to arrive. The corrugation wave in the disk. The detailed structure of the stellar halo, the identification of ancient mergers from the orbital patterns of halo stars, the half-light radius measurement that placed the Milky Way among its peers for the first time. All of these depended on Gaia. Gaia's contribution to Milky Way science is worth dwelling on, because it represents a qualitative change in what kinds of questions can be asked, rather than just a quantitative improvement in existing answers. Before Gaia, the standard question was, where are the stars? The answer came from photometric surveys, imaging the sky in multiple colors and identifying stars by their brightness and color. You could determine approximate distances from photometric parallax, comparing observed brightness to expected brightness for a star of a given type, and from period luminosity relations for pulsating stars. You could map overdensities and voids in the stellar population, but the uncertainties were large, especially at distances where the stars were faint. After Gaia, the question became, where are the stars? How far away are they? How fast are they moving? And in which direction? The answer is known to micro-arcsecond precision for the position, and to precisions that allow orbital reconstruction for millions of objects throughout the galaxy. The addition of velocity information transforms what is possible. Position alone tells you where something is. Position plus velocity tells you where it is going and where it came from. From the current state of a stellar orbit, you can reconstruct its past trajectory, how it has moved over millions and billions of years, and trace it back to its origin. This is how the Gaia Sausage Enceladus merger was identified, not by directly observing the collision, which happened billions of years ago, but by recognizing that the current orbits of a large population of halo stars are consistent with what would result from such a collision. Gaia gave astronomers a window into the past. The current positions and velocities of stars carry encoded information about the events that put them in those orbits. With sufficient precision, which Gaia provided, that information can be decoded, but Gaia's satellite has also produced results that were not originally anticipated when it was designed. One example is the detection of so-called runaway stars moving through the galaxy at velocities so high that they were clearly ejected from some violent event, possibly a supernova explosion that disrupted a binary star system, or a close encounter near the galactic center. Gaia's proper motion measurements are precise enough to trace these stars backward in time and identify where they originated. Another unexpected result was the detection of a population of stars moving in streams through the galaxy that turned out to be the debris of globular clusters, dense balls of ancient stars that orbit the Milky Way, gradually being disrupted by the galaxy's tidal field over billions of years. Each globular cluster, as it is slowly torn apart, contributes a thin stream of stars to the halo. Gaia found dozens of these streams, many previously unknown. A third unanticipated result was a sharp feature in the distribution of stellar velocities in the solar neighborhood, a grouping of stars moving at speeds just below the local escape velocity. This feature, called the Gaia Sausage in one of its original descriptions, later clarified to be related to the Gaia Sausage-Enceladus merger, was only recognizable in the precise velocity data that Gaia provided. The satellite was designed to be a star mapper. It became an instrument of galactic archaeology. There is a number that astronomers use to compare the sizes of galaxies across the universe, not the diameter of the disk, which depends on where you draw the boundary. Not the extent of the stellar halo, which fades gradually rather than ending sharply. A number that can be applied consistently to any galaxy regardless of its shape or the assumptions used to model it. That number is called the half-light radius. The half-light radius is the radius of a circle centered on the galaxy's center that contains exactly half the galaxy's total light output. It does not require assuming anything about how the density of stars changes with distance. It does not depend on where you draw the edge. You simply add up all the light coming from the galaxy and find the radius at which you have accumulated half of it. For external galaxies, measured from the outside with a single image, this is a straightforward calculation. For the Milky Way, measured from the inside with a piecemeal dataset, it was not straightforward at all. For decades, attempts to measure the Milky Way's half-light radius produced a number that was puzzlingly small, consistently smaller than what would be expected for a galaxy of the Milky Way's stellar mass. When plotted against other disk galaxies of similar mass on a size-mass diagram, the Milky Way appeared to be unusually compact, sitting below the average relation for galaxies like it. This was known but unresolved. Some astronomers suspected the measurement was biased. Others wondered if the Milky Way was genuinely unusual in some way. In June 2024, a team of researchers published a new measurement that resolved the discrepancy. The study, authored by Lian and colleagues, used Gaia data to construct the surface brightness profile of the Milky Way's disk across an unprecedentedly wide radial range from the galactic center outward to roughly 17 kiloparsecs, or about 55,000 light-years. They broke the stellar population down by age, tracing how the brightness profile changes for stars of different ages separately. This age-result approach revealed something that earlier analyses had missed. The inner disk does not follow a simple exponential profile. Between roughly 11,000 and 24,000 light-years from the center, the surface brightness is nearly flat. The density does not decrease with radius as quickly as a simple exponential would predict. This inner flattening changes the calculation of the half-light radius significantly. The flat inner region means that a larger fraction of the galaxy's light is concentrated at intermediate radii, rather than falling steeply toward the center. When the half-light radius is calculated using this more accurate broken profile, it comes out larger. The result? A half-light radius of 5.75 kiloparsecs with an uncertainty of plus or minus 0.38 kiloparsecs. 5.75 kiloparsecs is approximately 18,750 light-years. when this value is plotted on the size-mass diagram alongside other disk galaxies of similar mass, the Milky Way falls squarely in the middle of the distribution. Not an outlier, not an unusually compact galaxy, but a typical disk galaxy of its mass. The Milky Way is not strange. Previous measurements were using the wrong model for the disk's profile, which produced a biased, underestimated size. The new measurement, using Gaia's detailed data and an age result analysis, corrected this bias. For the first time, the Milky Way could be compared on equal terms to the thousands of external disk galaxies that have been measured the same way. This is the finally in the title. Not that the Milky Way's size was completely unknown before, but that the specific measurement needed to place it fairly among its peers was now, for the first time, in hand. The half-light radius measurement also resolved a puzzle that had been bothering galactic astronomers for years. The puzzle is sometimes called the Milky Way's size anomaly. When astronomers catalogue disk galaxies in the universe and compare them by stellar mass and size, they find a tight correlation. More massive galaxies tend to be larger. This mass-size relation holds across many orders of magnitude in galaxy mass and has been measured for thousands of galaxies in various surveys. For most of this history, when astronomers tried to place the Milky Way on this diagram, using the various estimates of its stellar mass and its scale length, it appeared below the average relation. It appeared too small for its mass. Not dramatically so, but consistently. The Milky Way was a compact galaxy, sitting below where a typical galaxy of its mass should be. Several explanations were proposed. Perhaps the Milky Way truly is more compact than average, an unusual galaxy in this specific dimension. Perhaps the estimates of its mass were wrong in a systematic way. Perhaps the scale length was being measured differently for the Milky Way than for external galaxies, introducing a bias. The 2024 measurement resolved this by identifying the bias. The scale length approach systematically underestimates the Milky Way's size because it uses a single exponential model that misses the inner disk's flattened profile. The half-light radius, which is model-independent and directly comparable across all galaxy types, places the Milky Way right where it should be on the mass-size diagram. The size anomaly was not real. It was a measurement artifact. This resolution is more than just a number corrected. It means the Milky Way is a typical galaxy, not an outlier, not a special case, but a representative example of the class of disk galaxies of its mass. Its size history, its growth trajectory, its structural properties, all of these can now be compared to the broader population of disk galaxies in a way that was not straightforwardly possible when it appeared to be anomalously compact. The concept of measuring the Milky Way from the inside also connects to a deeper question in science. How do you study a system you are part of? This is a problem that appears in many contexts. A sociologist studying their own society faces it. A historian studying their own era faces it. An economist studying the economy they live in faces it. In all these cases, the observer's embeddedness in the system they are studying both provides access. You can see things from the inside that an outsider cannot, and introduces bias. You cannot see the whole system at once. For Milky Way astronomy, the inside position provides some genuine advantages. We can study individual stars in the Milky Way at a level of detail impossible for external galaxies. Their spectra, their orbits, their ages, their chemical compositions at high resolution. We can send spacecraft to study the solar neighborhood directly. We can use radio and infrared techniques to penetrate the dust that would not obstruct an external observer, but would obstruct an optical observer from the outside. But the bias of the inside position is real and significant. We cannot see the full extent of the disk in a single image. The zone of avoidance is genuinely opaque. The structure of the far side of the galaxy is inferred rather than directly observed. The solution has been exactly what Gaia and the spectroscopic surveys represent: instruments that compensate for the inside position by measuring properties of individual stars, their distances, velocities and chemistries across the full sky, and then reconstructing the galaxy's three-dimensional structure from those individual data points. The measurement is more laborious than photographing an external galaxy, but the result is richer in certain dimensions. The stars are not the only thing in the disk. Between the stars, filling the spaces that look empty to the naked eye, there is gas. And the galaxy's gas disk extends even further than the stellar disk. Most of this gas is hydrogen, the most abundant element in the universe. also the most abundant gas in the Milky Way. It exists in several forms. In the hot diffuse regions between stars, hydrogen is ionized, its electrons stripped away by the ultraviolet radiation from nearby hot stars. In denser clouds, hydrogen is molecular, two hydrogen atoms bound together into a molecule, and in the extended outer disk, hydrogen exists primarily in its neutral atomic form, a single proton with a single orbiting electron, drifting through space at temperatures just a few tens of degrees above absolute zero. This neutral hydrogen has a particular quality that makes it invaluable to astronomers. Under specific conditions, a neutral hydrogen atom occasionally flips the spin of its electron relative to the spin of its proton from parallel to anti-parallel and releases a photon in the procell. The photon has a wavelength of exactly 21 centimeters. This is a radio wavelength, and it passes through interstellar dust virtually without absorption. The 21 centimeter line, as it is called, was first predicted theoretically in 1944 and first observed in 1951, when radio astronomers turned their instruments toward the sky and tuned to 21 centimeters. They could suddenly map the gas distribution of the Milky Way in directions where optical astronomy was completely blind. The galactic plane, which is opaque to visible light in many directions because of dust, is transparent to 21 centimeter radio waves. The first maps of the Milky Way's spiral arms came from 21 centimeter observations. The first detection of the galactic disk walk came from these same maps. The neutral hydrogen disk extends to a diameter of approximately 228,000 light-years, larger than the stellar disk's estimated 200,000 light-years, though not dramatically so. More notably, the neutral hydrogen disk shows the warp more clearly and at larger scales than the stellar disk does. The gas follows the disk's bent shape out to greater distances, providing a cleaner tracer of the outer disk's geometry. Beyond the edge of the neutral hydrogen disk, the ordinary matter of the galaxy, stars, gas, dust, effectively ends. There are isolated stars and sparse streams of gas at greater distances, but the organized disk structure terminates at roughly this distance from the center. What lies beyond is a different kind of structure, one that contains no light, emits no radio waves, and was completely invisible to all of astronomy until its gravitational influence began to be inferred indirectly from the motions of things that can be seen. The 21 centimeter hydrogen line has a long history as a tool for mapping the galaxy structure, and its discovery was one of the pivotal moments in the history of radio astronomy. The prediction that neutral hydrogen would emit at 21 centimeters was made in 1944 by the Dutch astronomer Hendrik van der Hulst, who calculated the energy difference between the two spin states of the hydrogen atom and determined the corresponding photon wavelength. At the time, there was no way to detect the signal. The technology for sensitive radio receivers at that wavelength did not yet exist, but the prediction was taken seriously, and radio astronomers in the Netherlands, Australia, and the United States competed to make the first detection. The detection came in 1951, nearly simultaneously from groups in the Netherlands and the United States. Once the line was detected, its use as a galactic tracer was immediately obvious. Neutral hydrogen is distributed throughout the galaxy's disk in enormous quantities. Its radio emission passes through the dust that blocks optical observations, and the Doppler shift of the 21 centimeter line, the change in wavelength caused by the hydrogen's motion toward or away from Earth, allows measurement of the gas's velocity, from which its distance along the line of sight can be inferred using models of galactic rotation. This Doppler technique, called kinematic distance estimation, was used to produce the first maps of the Milky Way's spiral structure in the 1950s. The maps were rough by modern standards, but they confirmed that the galaxy is a spiral and revealed the approximate locations of the major spiral arms. They also revealed the warp in the outer disk. The 21 centimeter data clearly showed the hydrogen disk bending out of the galactic plane at large radii, giving astronomers their first evidence of the galaxy's non-flat geometry. The neutral hydrogen data remains one of the most complete data sets available for the structure of the outer Milky Way, where star densities are too low for most optical surveys to reach, but where hydrogen gas is still present and detectable. The gas disk and the stellar disk are related in a fundamental way. The gas is the raw material from which new disk stars form. When gas in the disk cools and becomes dense enough, gravity causes it to collapse into new stars. These new stars form in the plane of the disk, from gas that is already rotating with the disk, and they inherit the disk's chemical properties from the gas they form from. Star formation in the disk is therefore a continuous process that has been operating for most of the galaxy's history, gradually converting gas into stars while simultaneously receiving new gas from the surrounding halo and from smaller galaxies absorbed over time. The outer disk, the region beyond roughly 80 to 100,000 light-years from the center, has a lower gas density and lower star formation rate than the inner disk. But star formation does occur in the outer disk, and some of the disk stars found at large distances in the spectroscopic surveys are relatively young objects that formed from gas in the outer regions. The gas disk's extent beyond the stellar disk is an indication that the galaxy's star formation might continue outward in the future as conditions in the outer disk change. The gas is there. Whether it will form stars efficiently depends on the local conditions, gas density, temperature, the presence of stabilizing or destabilizing gravitational perturbations. The current state of the gas disk is therefore not just a measure of the galaxy's past, it is also a hint about its future. The outer gas disk represents a reservoir of potential star formation that the galaxy has not yet used. The visible Milky Way, its stars, its gas, its dust, everything that emits or reflects light, is surrounded by something that contains no light at all. Call it the dark matter halo. Not because the name explains what dark matter is, it does not. That remains one of the most important unsolved questions in all of physics. But because it describes what can be observed about it. The halo is a region of space surrounding the galaxy where something with mass exists, exerting gravitational force without producing any electromagnetic radiation that current instruments can detect. The evidence for this component is not subtle. It is written into the rotation curve of the galaxy. When you observe a spiral galaxy, you can measure how fast the stars at different distances from the center are orbiting. In a simple system, one where most of the mass is concentrated in the central region, orbital speed should decrease with distance from the center. The way the planets in our solar system orbit more slowly the farther they are from the Sun. Mercury moves faster than Earth. Earth moves faster than Jupiter. Jupiter moves faster than Neptune. This is the expected pattern when the mass is concentrated at the center. For the Milky Way and for spiral galaxies generally, the rotation curve does not behave this way. The orbital speeds of stars in the outer disk do not fall off with distance. They remain roughly constant, flat, even at distances far from the center. This means there must be more mass further out than the visible stars and gas account for. Something invisible is adding gravitational mass at large radii, keeping the outer stars moving faster than they should if only the visible matter were present. That something is the dark matter halo. It surrounds the visible galaxy in a roughly spherical distribution, extending far beyond the disk and stellar halo. It contains roughly 5 to 10 times as much mass as all the visible matter in the galaxy combined, whatever its nature, and candidate explanations range from undiscovered particles to primordial black holes. Its gravitational reality is not in doubt. It holds the galaxy together in a way that the visible matter alone could not. How far does it extend? This is harder to measure than the visible components, precisely because you cannot see it directly. One approach uses the velocities of the Milky Way satellite galaxies, small dwarf galaxies orbiting at large distances. Bound satellites move faster and in more complex orbits. Satellites at the very edge of the galaxy's gravitational reach move differently from those well within it. At some distance, the galaxy's gravitational influence becomes indistinguishable from the general gravitational environment of the universe. In 2020, Alice Deason and colleagues at Durham University used exactly this approach. They analyzed the velocities of small satellite galaxies near the Milky Way using data from multiple surveys and compared the results to simulations of galaxy halos from the Illustris TNG cosmological simulation. They found that the velocity dispersion, the scatter in the velocities of satellite galaxies at different distances, drops sharply at a specific distance from the galactic center. This drop has the signature of the halo edge, the point where the dark matter halo density falls below the average cosmic density of dark matter. That edge falls at approximately 950,000 light-years from the galactic center. The total diameter of the Milky Way measured to this gravitational edge, is approximately 1.9 million light-years. 1.9 million light-years. 1.9 million light-years. The number that began at 100,000 has grown by a factor of 19. Set it against something familiar. The Andromeda Galaxy is about 2.5 million light-years away. If the Milky Way's gravitational edge is nearly 1 million light-years from our galactic center, and Andromeda's halo extends similarly from its center, the two halos are separated by only a few 100,000 light-years, possibly already overlapping a light-years. The Milky Way and Andromeda are not merely neighboring galaxies. They are already in gravitational contact, already influencing each other's outer structure, already beginning the slow process that will eventually bring them together. The dark matter halo's existence is inferred from multiple independent lines of evidence, and the convergence of these different approaches is what makes the inference robust. The rotation curve is the most well-known evidence, but there are others. Gravitational lensing is one. When light from a distant source passes close to a massive object, the gravitational field of the massive object bends the light path. The amount of bending depends on the mass along the line of sight. For the Milky Way, weak gravitational lensing of background galaxies can in principle be used to map the dark matter distribution, though the technique is more easily applied to external galaxies seen from the outside. The velocities of satellite galaxies provide another. Satellite galaxies are not fixed at a particular distance from the Milky Way. They orbit, following trajectories determined by the galaxy's gravitational field. If you can measure the velocities of satellites at various distances and compare them to what you would expect from the visible mass alone, the discrepancy reveals the additional dark mass. The Deason et al. 2020 study used exactly this approach to locate the halo edge. The Milky Way's escape velocity is another constraint. The escape velocity, the speed needed for an object to leave the galaxy's gravitational pull entirely, depends on the total mass within the orbit. Stars in the Sun's vicinity can be identified moving at near escape speeds, and from the distribution of their velocities the local escape velocity can be estimated. Combined with models of how the dark matter density varies with radius, this constrains the total dark matter halo mass. All of these independent approaches, rotation curves, satellite velocities, escape velocity measurements, gravitational lensing, and external galaxies, consistently point toward the same conclusion. Galaxies like the Milky Way are primarily dark matter by mass. The visible matter is a small fraction of the total. The halo is real. The dark matter halo measurement by Deason and colleagues used an approach that is worth understanding in some detail because it illustrates how galactic astronomy can probe structures that are completely invisible. The basic idea is that the satellite galaxies of the Milky Way are test particles moving under the influence of the galaxy's gravitational field. By measuring how fast they are moving at various distances from the Milky Way center, you can infer the gravitational force at those distances, and from the gravitational force, you can infer the mass enclosed within that radius. This is the same basic logic as the rotation curve argument, but applied to satellite galaxies rather than stars in the disk. For disk stars, orbital speeds can be measured directly from spectroscopy of the gas and stars rotating around the center. For satellite galaxies, the measurement is different. You need the full three-dimensional velocity, not just the line-of-sight component. Before Gaia, the transverse velocity of satellite galaxies, their motion across the sky, was poorly measured. Gaia's proper motion measurements changed this. For many of the Milky Way's known satellite galaxies, Gaia provided precise measurements of their motion across the sky, and combined with spectroscopic radial velocities, gave the full three-dimensional velocity. This enabled the velocity dispersion analysis that Deason and colleagues used to locate the halo edge. The result is that the dark matter halo's extent is not simply assumed or modeled in from theory. It is observationally constrained by real data on real satellite galaxies measured with real instruments. The halo is vast, and its extent is now measured rather than guessed. The revised size of the Milky Way changes how the galaxy relates to its neighborhood. The local group, the name given to the gravitationally bound collection of galaxies that includes the Milky Way and Andromeda, spans roughly 10 million light-years in total diameter. Within this volume, roughly 50 galaxies have been identified. Most of them are small, dwarf irregular galaxies, dwarf spheroidal galaxies. ultra-faint dwarf galaxies discovered only recently in deep survey data. A few of the most visible are the Large and Small Magellanic Clouds, two irregular dwarf galaxies visible from Earth's southern hemisphere as bright patches of light separated from the main Milky Way band. The Milky Way and Andromeda jointly dominate the local group. Together they contain the overwhelming majority of its total mass. The smaller galaxies are distributed around these two dominant systems, some orbiting the Milky Way, others orbiting Andromeda, still others on more independent trajectories through the local group. For most of astronomical history, Andromeda was considered the larger of the two. Its stellar disk is visually more extended, its central bulge more prominent, its satellite system more numerous and better studied. The Milky Way, as the smaller partner, was assumed to have a proportionally lower mass and gravitational reach. This assumption has been steadily eroded by improved measurements. The two galaxies are now understood to be broadly comparable in mass and stellar content, with the precise comparison depending on which estimates of the dark matter halo mass are used. Estimates that still carry significant uncertainty. What is clear is that the Milky Way's dark matter halo extends to roughly 950,000 light-years in radius. This is large enough that the Milky Way's gravitational influence reaches a significant fraction of the distance to Andromeda. The two halos are likely already interacting. The merger that is often described as a future event due in approximately 4 to 5 billion years is, in a gravitational sense, already underway. The halos are not waiting for the luminous disks to collide. They are already touching. The Milky Way satellite system is also more extensive than once believed. The Large and Small Magellanic Clouds are the most prominent, but dozens of much smaller dwarf spheroidal galaxies are known to orbit at large distances. And surveys using Gaia data and dedicated deep imaging programs continue to find new ultra-faint satellite galaxies, objects so dim that they contain only a few thousand stars and were completely invisible to earlier instruments. The number of known Milky Way satellites has grown from a handful in the mid-20th century to over 50 confirmed systems, with theoretical predictions suggesting dozens or hundreds more may remain undiscovered at very low surface brightness. The galaxy is not just larger than the Skoob diagram. Its influence, its satellite system, and its gravitational reach all extend considerably further than the familiar image suggests. The question of whether the Milky Way or Andromeda is larger has been debated for decades and is not yet fully settled. For most of the 20th century, Andromeda was considered the dominant partner. It is visually more extended. Its central bulge is more luminous. Its satellite system includes several relatively bright, dwarf elliptical galaxies that are visible to the naked eye in very dark skies. When the Milky Way's apparent compactness was still being attributed to real structural differences rather than measurement bias, Andromeda was thought to be substantially larger and more massive. More recent measurements have complicated this picture. The Milky Way's stellar mass estimates have been revised upward as its disk extent was revised. Its dark matter halo mass is comparable to Andromeda's in most studies. Some analyses suggest the Milky Way may actually be slightly more massive than Andromeda. Others favor the reverse. The honest answer is that the two galaxies are broadly comparable, with remaining uncertainties that prevent a confident declaration of which is larger. This near equality has implications for the future of the local group. In approximately 4 to 5 billion years, the Milky Way and Andromeda will collide and begin merging. The detailed dynamics of the merger, which galaxy's core survives at the center of the merged system, how the stars are redistributed, how much star formation is triggered, depends sensitively on the mass ratio of the two galaxies. A perfectly equal merger produces different outcomes than a merger where one galaxy is 50% more massive than the other. The uncertainty in relative masses translates directly into uncertainty about what the merged galaxy will look like. What is clear is that both galaxies are major contributors to the local group structure and future. The Milky Way is not a junior partner to Andromeda. It is a near equal, and the local universe is organized around the gravitational interplay between them. The local group structure has one more feature worth noting that becomes clearer with a revised understanding of the Milky Way's size. The local group is not the only gravitationally bound galaxy group in the nearby universe. It is part of a larger structure, the Virgo supercluster, also called Laniakea, which encompasses dozens of galaxy groups and clusters within a volume of roughly 500 million light-years. The Virgo cluster, the nearest large galaxy cluster, is about 55 million light-years away and contains more than 1,000 galaxies. The local group and nearby galaxy groups are moving toward the Virgo cluster at roughly 200 kilometers per second, drawn by its gravitational pull. Whether this inflow will eventually result in the local group merging into the Virgo cluster depends on whether the local group is gravitationally bound to the Virgo cluster or merely moving through the Hubble flow near it. Current estimates suggest the local group is not bound to the Virgo cluster. It will approach but not merge on cosmological timescales. The Milky Way's dark matter halo, at nearly 2 million light-years in diameter, is a significant gravitational structure in this context. Its influence reaches out far enough to interact gravitationally with other galaxies in the local group beyond just Andromeda. The positioning of the Milky Way and its halo within the larger structure of the local group and the nearby supercluster is part of the context that determines how the galaxy's history will continue to unfold. The size the Milky Way has today did not arrive all at once. The galaxy grew, and the evidence of how it grew is written into the positions and velocities of its stars. Galaxies grow in two primary ways. They form stars from their own gas, an internal process driven by cooling and gravitational collapse of the galaxy's own material, and they absorb other galaxies, an external process in which smaller systems fall into the gravitational well of the larger galaxy and are disrupted, their stars joining the larger system structure. Both processes have operated throughout the Milky Way's history, but the second process, accretion of smaller galaxies, has left its mark in a way that is now, with Gaia's data, directly readable from the current state of the galaxy. In 2018, astronomers analyzing the first major release of Gaia data noticed something specific about the orbital characteristics of stars in the interstellar halo. A large fraction of these stars had unusual orbits, highly radial, meaning their paths were strongly elongated toward the galactic center rather than following the more circular orbits typical of disk stars. Stars with this orbital pattern are characteristic of material accreted in a head-on collision. When a galaxy falls into the Milky Way on a roughly radial path, its stars are shredded and scattered, but they retain a memory of the inflow direction and the elongated shape of their subsequent orbits. The cluster of radially biased halo stars pointed to a specific ancient merger, a dwarf galaxy that fell into the Milky Way approximately 8 to 11 billion years ago on a roughly head-on trajectory. The event is called the Gaia-Sausage-Enceladus merger, named after the elongated shape of the stellar distribution in orbital energy space that identifies the merger debris. The infalling galaxy was not tiny, it was a significant system, probably carrying a few hundred million solar masses in stars alone, and several times that in dark matter. Its disruption likely deposited a major fraction of the interstellar halo and may have heated and thickened the Milky Way's disk at the time. The Gaia-Sausage-Enceladus merger was not the only ancient accretion event. Other clusters of stars in the halo point to other past mergers, smaller systems absorbed at different times from different directions. The Helmi streams, the Sequoia event, the Thamnos substructure. Each is an identified population of halo stars tracing back to a specific ancient galaxy that no longer exists as an independent system. The stellar halo is not a uniform ancient remnant. It is a layered archive of the Milky Way's merger history, and Gaia's precision gave astronomers the ability to read it. The 2024 half-light radius measurement added another dimension to this history. By analyzing the age-resolved surface brightness profile, the team found that the Milky Way's size history, how its half-light radius has changed over cosmic time, is broadly consistent with other disk galaxies at high redshift, suggesting that the galaxy grew through relatively normal processes. It likely experienced inefficient secular growth, meaning it did not grow as quickly as some models predicted, and its current size was reached through a gradual accumulation rather than a single transformative event. The Milky Way grew by absorbing, the halo carries the record, and the size the galaxy has today is the accumulated result of 4.5 billion years of consuming smaller systems while continuing to form new stars from its own gas. The Gaia Sausage and Enceladus merger discovery is particularly significant because it showed that even the galaxy's internal structure carries information about events that happened billions of years ago. This is a form of galactic archaeology. Just as terrestrial geology reads the history of Earth's climate from ice cores and rock strata, galactic astronomy can read the history of the galaxy's mergers and accretion events from the current state of its stellar populations. The key to this technique is the principle that stars largely conserve their orbital properties. When a star forms in a small galaxy, and that galaxy is later absorbed by the Milky Way, the star's orbit changes dramatically during the disruption. But the debris from all the stars of the original galaxy shares a similar range of orbital properties reflecting the orbit and mass of the progenitor galaxy. If you can identify a population of stars with coherent orbital properties, similar orbital energies, similar orbital shapes, you can infer that they came from a common progenitor. The Gaia Sausage and Enceladus stars are identifiable precisely because they have a distinctive orbital signature, high orbital eccentricity, meaning their orbits are elongated toward the galactic center rather than roughly circular. This pattern is what you would expect from the debris of a galaxy that fell into the Milky Way on a radial head-on trajectory. The infalling galaxy's stars were scattered and shocked, but they retained enough memory of the infall direction to appear coherent in orbital energy angular momentum space. Since the initial identification of Gaia Sausage and Enceladus, several other ancient merger events have been identified using the same technique. Each one is a named remnant, a stellar population with a specific orbital fingerprint pointing to a specific ancient progenitor. The stellar halo, once thought to be a structureless background of ancient stars, is now understood to be a complex, layered record of the galaxy's history of assimilation. The Sagittarius dwarf merger, still ongoing, provides the only real-time view humans have of the process that built the stellar halo over billions of years. The Sagittarius dwarf galaxy was discovered in 1994, relatively recently in the history of Milky Way studies. It had evaded detection for so long because it lies almost directly behind the galactic center. From Earth's perspective, in the region of sky heavily obscured by the Milky Way's own disk, once it was found, its properties were striking. It is one of the closest satellite galaxies to the Milky Way, and it is currently being torn apart by tidal forces. The Sagittarius stream, the ribbon of stars being stripped from the dwarf galaxy, has been traced across much of the sky. It wraps around the Milky Way in at least 2 loops, representing material stripped during 2 separate orbital passages. Stars in the stream span a range of distances from the galactic center, spread along the path of the original galaxy's orbit. The stream contains stars of various types. Red giant branch stars, which are bright and identifiable spectroscopically, have been extensively used as tracers. Their chemical compositions carry the signature of the Sagittarius dwarf galaxy's star formation history rather than the Milky Way's, making them distinguishable from local discal halo stars. This ongoing disruption gives astronomers a calibration point. The properties of the Sagittarius stream, its width, its chemical gradient along the orbit, its density variation can be compared to simulations of what a dwarf galaxy of a given mass would produce when disrupted. This comparison constrains both the mass of the Sagittarius progenitor and the shape of the Milky Way's gravitational potential through which it is orbiting. The measurements have converged, but convergence is not the same as completion. The Milky Way's size is better known today than it has ever been. The stellar disk, approximately 200,000 light-years across, the stellar halo, roughly 400,000 to 600,000 light-years in diameter, with outlier stars at even greater distances. The neutral hydrogen gas disk, approximately 228,000 light-years. The dark matter halo edge, approximately 1.9 million light-years in total diameter. These numbers are the product of decades of improving instruments and methods, and they are substantially more reliable than the estimates that preceded them. But there are specific gaps that remain, and they are worth naming honestly. The total mass of the Milky Way, including its dark matter, is still uncertain by roughly a factor of 2. Different studies using different methods and different assumptions about the dark matter halo's shape and extent produce estimates ranging from roughly 700 billion to nearly 2 trillion times the mass of the Sun. The uncertainty in the total mass propagates into uncertainty about the number of satellite galaxies the Milky Way should host, the precise timing and dynamics of the future Andromeda merger. and how the galaxy will evolve over the next several billion years. The zone of avoidance remains a significant problem. The plane of the Milky Way's disk, the region of sky behind the disk itself, where dust extinction is highest, is still largely opaque to optical telescopes. Behind this band, entire galaxy clusters and large-scale structures are hidden. In 2025, a galaxy supercluster was discovered in the zone of avoidance, with a total mass equivalent to 30,000 trillion solar masses. The supercluster had been invisible to optical surveys entirely. Its discovery by infrared and radio techniques demonstrated that even the immediate extragalactic surroundings of the Milky Way are still being mapped. The number of ultra-faint satellite galaxies orbiting the Milky Way is also unresolved. Theoretical predictions from simulations of galaxy formation suggest that a Milky Way mass-dark matter halo should host hundreds of small satellite systems. Current observations have confirmed roughly 50. Whether the missing hundreds are simply too faint to detect yet, or whether the simulations are overestimating the satellite count, is one of the most active debates in galactic astronomy. Gaia's successor missions and the next generation of large telescopes, particularly the Vera C. Rubin Observatory's 10-year legacy survey of space and time, are expected to discover many of the missing satellites if they exist. The outer stellar halo is poorly characterized beyond roughly 400,000 light-years. Individual stars have been found at greater distances, but whether these extreme outliers follow the same density profile as the inner halo or represent a separate outer halo population is not yet resolved. The halo's shape, whether it is spherical or flattened, aligned with the disk or the dark matter halo, is also not precisely known. The finally in the title is real. The measurements are substantially better than they were. The converging picture of a galaxy with a 200,000 light-year stellar disk, a stellar halo extending to 500,000 light-years, and a dark matter halo approaching 2 million light-years is a genuine scientific achievement, but the specific numbers carry uncertainties, and the outer regions of the galaxy remain, in specific ways, incompletely characterized. The zone of avoidance is one of the most enduring obstacles in Milky Way science, and its effects extend beyond what is visible in the night sky. The zone, defined roughly as the band of sky within 10 to 20 degrees of the galactic plane, is problematic for optical astronomy because dust in the disk absorbs and scatters visible light so heavily that even nearby galaxies behind the dust are invisible or severely dimmed. The optical depth through the galactic plane in some directions is so high that only a fraction of a percent of the light from background objects reaches Earth. Radio and infrared techniques can penetrate this zone more effectively. The 21 centimeter hydrogen line passes through dust almost without absorption. Near and mid-infrared light is less attenuated than visible light. These wavelengths have revealed structures in and behind the zone of avoidance that were completely invisible to optical surveys. The galaxy supercluster discovered in 2025 hiding in the zone of avoidance is a striking example of how much the zone still conceals. A structure containing 30,000 trillion solar masses, comparable to the largest known superclusters, was invisible to generations of optical surveys and was found only because of targeted infrared and radio observations. It is not a distant object. It is in the immediate extragalactic neighborhood of the Milky Way, simply hidden by the galaxy's own dust. This has implications for our understanding of the local large-scale structure. The gravitational influence of hidden structures behind the zone of avoidance may be contributing to the observed motions of local galaxies in ways that have been hard to account for. The Great Attractor, a region of concentrated mass toward which the local group and many surrounding galaxy groups appear to be moving, may have contributions from structures not yet fully mapped because of the zone. The discovery of the zone of avoidance supercluster in 2025 is a reminder that large-scale structure can be hidden in plain sight, or rather, hidden in obscured sight. The supercluster, identified by infrared and radio surveys capable of penetrating the galactic dust, contains the equivalent of 30,000 trillion solar masses, a number so large that ordinary comparisons struggle to convey it. The total mass of the Milky Way, including its dark matter halo, is estimated at roughly 1 to 2 trillion solar masses. The newly discovered supercluster is therefore equivalent to tens of thousands of Milky Way-scale structures, Its presence behind the zone of avoidance means that for most of the history of optical astronomy, this enormous concentration of mass was simply invisible. Astronomers knew something significant might lurk in the zone. The direction toward the galactic center has long been suspected to contain unaccounted-for mass based on the peculiar velocities of nearby galaxies, but the specific structure, its extent, and its mass were not directly characterized until recent infrared and radio surveys made it accessible. This is not the first time a significant structure was found hiding in the zone of avoidance. The Great Attractor, a massive concentration of galaxies toward which the local group and surrounding galaxy groups are moving, is partially obscured by the zone, which made its characterization difficult for decades. As survey techniques improve and more sensitive infrared and radio instruments come online, the zone is gradually being mapped. But it remains the largest blind spot in our optical view of the nearby universe. Stand outside on a clear night and let your eyes adjust. The band of the Milky Way appears overhead in its full arc. The brightest portion, in the direction of Sagittarius, is the galactic center, the densest concentration of stars in the disk, where the supermassive black hole called Sagittarius A star sits behind 30,000 light-years of intervening stars and dust. The fainter, more diffuse regions of the band are directions along the disk at greater distances from the center or toward the outer disk where the star density is lower. You are at a specific position within this structure, roughly 26,000 light-years from the galactic center. Inside the stellar disk, which extends to about 100,000 light-years from the center in your direction before the density drops below any reasonable definition of a disk, your position is not special in any particular way. It is not near the center, not near the outer edge, not in an unusually dense or unusually sparse region. It is a middle latitude in a middle arm of a spiral galaxy. The stars you can see with the naked eye, the entire populated night sky, are all within a few thousand light-years of Earth. Even the most distant stars visible without optical aid are less than 0.5% of the way across the stellar disk. The arc of the Milky Way itself, which looks so vast overhead, contains stars mostly within 2,000 to 30,000 light-years. The disk extends far beyond what the eye perceives. Above and below you, extending for hundreds of thousands of light-years in every direction perpendicular to the disk, the stellar halo drifts in ancient orbits. You cannot see it from the ground without a telescope. The individual stars are too sparse and too dim against the sky background. But it is there, surrounding the disk, ancient and diffuse, and surrounding everything, the disk, the stellar halo, the gas, everything made of ordinary matter. The dark matter halo extends outward to nearly 1 million light-years in every direction. It is invisible. It emits nothing, but it is the dominant mass of the system you live in. The galaxy you inhabit is not primarily a spiral of stars. It is primarily a sphere of dark matter, with a thin spiral of stars inside it. The band of light overhead is your immediate neighborhood. The real galaxy extends 1,000 times further in every direction. The experience of standing inside the Milky Way has a specific character that is worth pausing on, because it is the starting point for everything in this script. The galaxy is not something you look at from a distance, it is something you are embedded in. This creates an unusual phenomenology, the experience of being inside something so large that its structure is difficult to perceive directly. Consider the night sky from a dark location. The stars you see span the entire observable range of your unaided vision, from the very nearest stars a few light-years away to the most distant stars visible to the naked eye. Perhaps a few thousand light-years. This entire range, the bright sky you see on a clear night, is a negligibly thin slice of the galaxy's total extent. The disk extends 100,000 light-years in the direction you face. The stellar halo extends further still. The dark matter halo extends to nearly 1 million light-years in every direction. None of this is directly perceptible. What you see when you look up is not the galaxy. It is a sliver of the galaxy's nearest volume. The galaxy itself is everywhere around you above a bow, ahead, behind, but its structure, the pattern of its arms, the extent of its disk, the dimensions of its halo, is invisible to the unaided eye because you are inside it and because the observable range of human vision is a tiny fraction of the relevant scale. This is not a failure of perception. It is simply a consequence of the relationship between scale and position. A person standing in the middle of a continent cannot see the continent's coastlines. A person standing in the middle of the galaxy cannot see its boundaries. The galaxy's size was always there. The tools that revealed it are recent. The experience of looking up at the Milky Way from inside has a specific psychological dimension that is worth acknowledging. The galaxy is not abstract, it is visible. On a dark night, the band of the Milky Way is directly observable, occupying the full arc of the sky in a way that leaves an impression. But the gap between what you see and what you know is enormous. What you see is a band of faint light, an aggregate of millions of individual stars too numerous to resolve, seen as a wash of glow against the dark sky. What you know after tonight is that this band is the plane of a disk 200,000 light-years across, warped and flared at its edges, surrounded by a stellar halo extending to 500,000 light-years, and wrapped in a dark matter halo nearly 2 million light-years in diameter. The band looks local because the brain is calibrated for everyday scales. The sky looks big but comprehensible. The stars look scattered but finite. The arc from horizon to horizon looks like a large but knowable thing. The galaxy's actual scale is entirely outside this calibration. There is no experiential equivalent for the difference between the few thousand light-years visible in the band and the hundreds of thousands or millions of light-years that define the galaxy's true extent. The number does not land as felt scale. It lands as conceptual scale, something you understand but do not experience. This gap between the visible and the known is the normal condition of large-scale astronomy. The universe is not designed for human intuition, but standing under the Milky Way band and holding both the visible and the known, simultaneously, the familiar arc of light and the invisible structure it represents, is the closest to direct experience of the galaxy's true nature that the inside position allows. Everything described in this script can be organized around a single observation. The Milky Way does not have one size. It has layers, and each layer is defined by different physics. The innermost and brightest layer is the dense stellar disk, the region where star formation has been most active, where the spiral arms trace the density waves through the gas where most of the galaxy's current star-forming activity takes place. 200,000 light-years across, 1,000 light-years thick at the Sun's position, flaring to greater thickness at the outer edges. The next layer outward is the stellar halo, the diffuse cloud of ancient metal-poor stars following elongated orbits around the galaxy's center. 400,000 to 600,000 light-years in diameter. Sparse, old, rich with the debris of galaxies absorbed over billions of years. The next layer is the gas disk, the extended reservoir of neutral hydrogen that traces the disk's warp and provides the raw material for future star formation. 228,000 light-years across, slightly larger than the stellar disk but following its geometry. And surrounding all of this, invisible dominant vast, the dark matter halo, approximately 1.9 million light-years in diameter, containing 5 to 10 times as much mass as all the visible matter combined. The true container in which everything else exists. These are not 4 definitions competing to describe the same object. They are 4 real, distinct physical structures that together constitute what we call the Milky Way galaxy. The answer to how big the Milky Way is depends on which structure you are measuring, and any honest answer to the question must specify which layer it is talking about. The 100,000 light-year schoolbook number refers to the dense inner stellar disk, and is a real measurement of a real thing. The 200,000 light-year number refers to the full extent of the stellar disk as confirmed by spectroscopy. The 500,000 light-year number refers to the stellar halo. The nearly 2 million light-year number refers to the dark matter halo's gravitational edge. Each number is right. Each is right about something different. What the discovery of the Milky Way's true size reveals is not just a larger number, it reveals what a galaxy is. A galaxy is a layered gravitational structure. Its visible, stellar component is the most familiar and easiest to measure, but it is a fraction of the total. The dark matter halo is the primary container. The stellar halo is the archaeological record of the galaxy's growth through mergers. The gas disk is the reservoir of future stars. The stellar disk is where most of the current action happens. Understanding the Milky Way as a layered structure, rather than a disk of stars with a fuzzy edge, is a fundamental shift in how to think about what galaxies are and how they work. And it took the specific convergence of tools that only recently existed. Gaia's billion-star catalogue, the spectroscopic surveys that could trace stellar populations to the outer disk, the simulations that predicted what the dark matter halo edge should look like, the studies of satellite galaxy velocities that could detect where the halo ends. The title says we finally discovered how big the Milky Way is. What we really discovered is what the Milky Way actually is. The answer to how big the Milky Way is has changed because the question has changed. Early measurements asked, where does the visible disk end? The answer was 100,000 light-years, and it was based on where the easily detectable stars became too sparse to find with the available instruments. Later measurements asked, where do disk stars stop appearing regardless of their density? The answer was 200,000 light-years, based on spectroscopic identification of disk members in the outer galaxy. Different measurements asked, how far does the galaxy's stellar content extend in 3 dimensions, including the halo? The answer was 400,000 to 600,000 light-years, based on tracing halo stars and stellar streams at large distances. Still other measurements asked, how large is the Milky Way compared to other galaxies of similar mass? Using a measurement standard that applies equally to all galaxies, the answer was a half-light radius of roughly 18,750 light-years, a number that placed the Milky Way firmly among typical disk galaxies rather than as an unusually compact outlier. And the most expansive measurements asked, where does the Milky Way's gravitational influence become negligible compared to the general cosmic background? The answer was roughly 950,000 light-years in radius, a total diameter of nearly 2 million light-years. Each question is legitimate. Each answer is real. The galaxy truly does have a dense inner disk of 100,000 light-years. It truly does have disk stars extending to 200,000. It truly does have a stellar halo extending to 500,000. It truly does have a gravitational reach of nearly 2 million. These are not contradictions. They are different aspects of the same multi-layered structure, measured with different techniques at different scales. The lesson is not that the old number was wrong and the new number is right. The lesson is that the galaxy is richer and more complex than any single number can capture, and that progress in understanding it comes from asking better questions as well as getting better answers. The 4 layers of the Milky Way: stellar disk, stellar halo, gas disk, dark matter halo, each have their own dominant physics that explains why they are the size they are. The stellar disk is the size it is because of angular momentum and cooling. Gas falling into the young galaxy carried angular momentum, rotational motion, that prevented it from collapsing all the way to the center. Instead, it settled into a rotating disk with different radii corresponding to different amounts of angular momentum. More angular momentum means a larger disk. The disk formed where cooling was efficient enough to produce stars from the gas, and it extends to the distances where the combination of gas supply and cooling conditions allowed star formation to proceed. The stellar halo is the size it is because of the orbits of accreted material. When a small galaxy is tidally disrupted, its stars follow trajectories determined by the disruption dynamics and the host galaxy's gravitational potential. Radial inflow produces highly elongated orbits that carry stars far from the center. The halo's extent reflects both the orbital properties of accreted material and the mass of the host potential. The gas disk is slightly larger than the stellar disk because gas is collisional. It can spread and be transported by pressure gradients in a way that stars cannot. Gas can also be replenished from external sources. The dark matter halo is the size it is because of the conditions under which dark matter collapsed in the early universe. The dark matter halo formed first, before the visible matter, as a gravitational overdensity in the cosmic density field. Its size reflects the initial conditions of that overdensity and the subsequent growth through dark matter accretion. It is the original structure around which everything else assembled. There is something specific that happens when you understand the true size of the galaxy you live in. It is not merely that the number gets bigger. Numbers in astronomy are always too large for ordinary intuition. 100,000 light-years is already beyond comprehension in any experiential sense. 1.9 million light-years is bigger, but the additional largeness does not arrive as awe the way a first large number does. What arrives is something quieter. A repositioning. You are inside a structure that extends in every direction, above, below, and in the plane of the sky, to distances that dwarf even the familiar but staggering size of the solar system. The nearest star is 4 light-years away. The galactic center is 26,000. The edge of the stellar disk is roughly 100,000 light-years behind you in the direction away from the center. The edge of the stellar halo is perhaps 300,000 light-years further still. The edge of the dark matter halo is nearly 1 million light-years in every direction. At Voyager 1's speed, roughly 17 kilometers per second, reaching the edge of the dark matter halo would take approximately 17 billion years. The universe is currently about 13.8 billion years old. The Milky Way's gravitational reach extends to a distance that, at the fastest speed any human object has ever traveled, would take longer than the current age of the universe to cross. You are not on the edge of the Milky Way. You are not near its center. You are roughly halfway between the galactic center and the outer edge of the dense disk embedded in a spiral arm called the Orion Arm, inside a structure whose full extent was only recently understood by instruments launched within your lifetime. The band of light across the sky is one thin slice of that structure, the plane of the disk seen from the inside. The band looks vast because you are inside it and can see it spanning the whole sky, but the disk's true extent reaches far beyond what even the band suggests. And beyond the disk, the galaxy continues in layers for distances that make the band itself seem like a local thing. This is what the title delivers. Not a number revised upward, but a reframing of what you are inside. The Milky Way is not a flat spiral of stars that ends when the stars thin out. It is a layered gravitational system, dark matter dominant ancient halo surrounding gas and stars within, and the part you see on a clear night is the thinnest, brightest, most local slice of something that extends in every direction to nearly 2 million light-years. That band overhead, that familiar arc, it is the inside surface of something far larger than it looks. Good night. The specific number most worth carrying forward from tonight is not any single diameter. It is the relationship between the numbers. The visible band across the night sky, the dense plane of the disk, extends to roughly 200,000 light-years across. It is warped, flared and corrugated, alive with ongoing star formation and populated by hundreds of billions of stars in a rich diversity of ages and compositions. The stellar halo surrounds this disk, extending to 4 to 6 times the disk's diameter. It is ancient, metal poor, and structured with the remnants of galaxies absorbed over billions of years. It is sparse compared to the disk, but it occupies an enormous volume. The dark matter halo encloses everything. It contains the majority of the galaxy's mass. It is nearly 20 times wider than the luminous disk. It connects the Milky Way to Andromeda, already touching or nearly touching the dark matter halo of our eventual merger partner. These layers are not incidental. They reflect the physics of galaxy formation. The disk forms where gas cools and settles into a rotating plane. The stellar halo forms from early stars and captured debris. The dark matter halo is the original gravitational well that everything else collapsed into. The first structure to form, the last to disperse. Understanding the Milky Way's size means understanding that what we casually call the galaxy is actually a nested series of structures, each defined by different physics, each extending further into space than the one before it. The band of light across the sky is the innermost, most concentrated, most visible layer of a system that extends in every direction to distances that dwarf the solar system the way the solar system dwarfs a city block. You live not just on a planet in a solar system. You live inside a galaxy that surrounds you in every direction to a distance of nearly 1 million light-years, embedded within a universe that extends further still. The question of how big the Milky Way is turns out to be a way of asking, what are we actually inside? And the answer, finally measured with the tools available to this generation, is both larger and stranger than the diagram on the classroom wall ever suggested. The most important thing the revised size of the Milky Way conveys is not the number itself, but the nature of the question. Asking how big the Milky Way is not like asking how far it is from Earth to the Moon, where there is a single well-defined answer. It is like asking how big a city is, an answer that depends on whether you are measuring the city limits, the urban area, the metropolitan area, or the region of economic influence. Each measurement is real, each is useful for different purposes, and each gives a different number. The Milky Way's layered structure makes this multiplicity of answers not a sign of confusion, but a sign of the richness of the object being measured. A galaxy is not a simple sphere or disk with a clean boundary. It is a gravitational structure assembled over billions of years from gas, stars, and dark matter through processes that operate at different scales and leave different signatures at different distances from the center. The schoolbook diagram, a flat spiral with a clean edge at 100,000 light-years, captured one layer of this structure and presented it as the whole thing. The actual galaxy is at least 15 to 20 times larger in total extent, more complex in geometry, richer in history, and stranger in composition than the diagram suggested. This is not a failure of the diagram or of the science that produced it. It is the nature of how understanding deepens. The simple picture is a starting point. The deeper picture is what emerges when the tools are good enough to see past the starting point. What we finally discovered about the size of the Milky Way is not just how large it is how layered it is. And that is a discovery about what galaxies are, not fixed objects with clean boundaries, but gravitational processes extended across cosmic scales, still assembling, still evolving, still being measured.